Hi everyone! Today we're going to talk about Chapter 5, Higher Order Linear Differential Equations. So do you remember what we learned last chapter? So Chapter 1 was about first order differential equation. Okay, Section 1.3 we have the theorem of existence and uniqueness, and this theorem works for all kinds of first order differential equations, not necessarily linear. Okay, and then how do we solve differential equation? We know how to solve separable first order differential equation, and then for the first order linear differential equation we have the integrating factor technique to solve that. And when the right hand side looks like a composite function, we have the substitution method, right? A special case for that could be the homogeneous equations and the Bernoulli equations. Homogeneous equations, we let v be y over x. Bernoulli equations, we let v be y to the 1 minus n. Okay, so today we're gonna, instead of first order, we're gonna talk about higher order, but we mainly just focus on the linear differential equations. So we will talk about higher order, but we will more focus on the linear ones. Okay, so 5.1 is second order linear equations. So in the remaining sessions, we will talk about like higher order, maybe the third or the fourth. Okay. So review first order linear equations. So this is the general form. And we have the standard form. Okay. How do we get the standard form? So we make sure the coefficient of y prime is 1. So that's why both sides are divided by a1 of x. Okay, so after we get the standard form, then we have the integrating factor. Okay, so the integrating factor, our notation is mu. So mu of x is e to the integral of p of x dx. Okay, and what do? We use the integrating factor times y, that equals to the integral of q of x times the integrating factor. Okay, and how do we solve for y? We can both sides divided by the integrating factor, so then you can see this is like the same as multiplied by e to the negative integral of p of x dx. Okay, so and we can also find c using the initial condition y of x0 is y0. Okay, so here you can see the general solution is the particular solution plus the homogeneous solution. So this guy is the particular solution. This guy is the homogeneous solution. Okay, we use the notation yp to denote particular solution. And the particular solution, you can see it involves q of x. Okay, and the homogeneous solution, we use y sub h to denote that. And the homogeneous solution is the solution to the homogeneous problem, where it's like when the q of x is 0. So you can imagine when q of x is 0, so your solution won't have this part. It only has this guy, right? So that's why we say this term is the homogeneous solution. All right. So this is the theorem of existence and uniqueness for the linear first order equations. Okay, so we have the standard form y prime plus p of x times y equals to q of x. If p and q are continuous on the interval alpha to beta containing the initial value x0, then the theorem tells us that the initial value problem has a unique solution in at least the interval alpha to beta. Okay, so here are some notes. The region of validity of the solutions can be bigger than alpha to beta. And this theorem gives solution on the entire interval, whereas the old theorem, right, the theorem of existence and uniqueness in section 1.3 only gives solutions on a subinterval. And if you can remember the old theorem, we consider dy dx. So here, when we solve dy dx, it's minus p of x times y plus q of x, and we call this guy f of x. And we also look at partial f, partial y. And you can see when we took the derivative, partial f, partial y is the derivative of y is 1, so we only have the coefficient, which is minus p of x. Okay, so that's why if p and q are continuous, we get f, and partial y are also continuous. So actually, these theorems agree with our general theorem for all the first order differential equations. So we just need to look for an open interval where p and q are both continuous, and the problem points are singularities in the coefficients p and q and the forcing function q. Okay, so this is what we learned in chapter 1 about first order linear ODE. So now we're going to generalize these theorems to second order. Okay, so for second order linear differential equation, we also have the general form. And this is in order to get a standard form. We want to divide it by a2 of x. Okay? So, and then now we have the coefficients p, q, and g. So if all of them are continuous on the interval alpha beta containing the initial value x0, then same conclusion, the initial value problem has a unique solution at least alpha to beta. So here you can see second order, we actually need two initial conditions. So that's we need the y of x0 is y0. We also need y prime of x0 is y0. It's like, do you remember when you're given the acceleration, you integrate the acceleration, you get velocity, but you need the initial velocity to figure out the constant c, and you integrate the velocity one more time to get the displacement. And you also need to use the initial displacement to find the constant d. That's why second order, you need two initial conditions to figure out the constants c and d. All right, so it's time to look at our example 1. All right, so we want to find the interval where all the coefficient functions are continuous. So let me remind you what are the necessary concepts about this. So do you remember there are 3 types of functions with restricted domain? So what are those 3 types? First one, we have square roots. What do we need? We need the square root, the things inside the square root to be greater or equal to 0. Second, what is second? Fraction. What do we need? We need the things in the denominator not equal to 0. And the last one, we have natural log. And what do we need? We need a to be positive. All right. Okay, and then let's look at this problem. Do we have square roots? No, but we have fractions. So the first coefficient, we need the denominator not equal to 0. So x not equal to 1. The second one, we need the denominator not equal to 0. So x not equal to 2. The third one, we need the denominator not equal to 0, and so the x not equal to 4. Questions, do we care about the numerators? No, for the domains, if you want to find the x values where the functions are continuous, you don't need to look at the domain. Sorry, you don't need to look at the numerator, you only need to look at the denominator. Okay, so let's draw our real number line. So x cannot be 1. 1 is here. X cannot be 2. And x cannot be 4. Okay? So let's look at our initial value. Our initial value, x is 3. Where is 3? Right here. So we're actually at this piece. Okay, so on this piece. Okay, so we're actually on this piece. That is why find the interval on which a unit solution is guaranteed to exist by the theorem. So we know that a unique solution exists on these pieces 2 to 4. Okay, by the theorem. Okay. That is example 1. Let's look at example 2. All right, what is the first step? Do we just look at the coefficients? Sine x, other coefficients, sine x and cosine x. No, remember, what is the first step? The first step, you gotta make sure the our differential equation is a standard form, right? Okay, so y double prime plus cosine x over sine x, y prime equals to 5 over sine x. So the first step is make it into the standard form. So if you don't do it, oh my goodness, the whole problem, you get it wrong, right? Because if you just look at, you say the coefficient, sine, cosine is continuous everywhere. So then you would say, unit solution exists everywhere. But that's wrong. You don't have the standard form. So first step is you make it into the standard form. Okay, so now my coefficient is the cosine x over sine x and the 5 over sine x. What do we need? The denominator sine x. We require the denominator sine x is not equal to 0. Okay, and so sine x is like that. When do we have 0? Okay, when we have 0, pi, 2 pi, it means x cannot be k pi, where k is integer. All right. Okay, so now let's draw a picture. Cannot be 0, cannot be pi, cannot be 2 pi, cannot be minus pi. Okay, where is our initial value? X is minus 1. Where's minus 1? Somewhere here. So we're on this piece. Okay, so that's why we answer a unique solution exists on minus pi to 0. Okay, by the theorem. All right. Let's continue. So the next example, what is the first step? Well, are they in the standard form? Okay, maybe you can try to pause the video and try to work on it by yourself first, and then we continue to check our work. Okay, so how do we get rid of the coefficients? We both sides divided by 2 minus x to the 1/2. Oh, that is actually square root of 2 minus x. And then you should have x minus 2 on the top. But what is x to negative 2? It means the x is actually downstairs. Y prime equals y over square root of 2 minus x. Okay, and we're not in the standard form yet, because you gotta move all the y to the left hand side. So 2 minus x, x squared, y prime minus 1 over square root 2 minus x, y, and equal to 0. So actually this is a homogeneous equation. Okay, and then let's look at the coefficients. So this guy tells us that 2 minus x, because it's inside the square root, so it should be greater or equal to 0. But because it's in the denominator, it cannot be 0. So it means 2 minus x has to be greater than 0. And here, x squared in it, so x cannot be 0. And then here we get 2 greater than x, so x less than 2. Okay, so we have 0. x cannot be 0 to x is less than 2. Okay, what is our initial value? Oh my goodness, my initial value is at 2. So 2, see? 2, not good, not good. So that's why here, we don't expect a unique solution. So a unique solution is not guaranteed. Okay, so that's why a unique solution is not guaranteed to exist. Okay, by the theorem. Okay. All right, so that is example 3. Let's continue and look at example 4. Okay, so find the interval on which a unique solution is guaranteed to exist by the theorem. So let's make it into the standard form. Okay, so here we have okay, x y prime over 2 minus x minus 2y prime over 2 minus x equals to x minus 2 cubed over 2 minus x. Okay, so what is that? All right. Okay, let's see. We will say like, I get denominator 2 minus x, so 2 minus x cannot be 0. So x cannot be 2, so cannot be 2, but my initial value is at 2, so a unique solution is not guaranteed to exist. Okay, do you think about like that? Actually, this is wrong. Okay, let me show you why it's wrong. Okay, so let's put here, this guy is wrong. Okay, can you see actually there are 2 y prime? So actually you can group them together. You get y prime prime plus, when you group them together, you get x minus 2, 2 minus x, y prime. And actually on the right, you can see x minus 2 cubed, but what's 2 minus x? 2 minus x is actually negative x minus 2. Oops, so you can see here, this guy is actually x minus 2 over negative x minus 2. You can actually cancel it. So you get y prime prime minus y prime equals to negative x minus 2 squared. Okay. All right. So that's why the coefficient actually continues everywhere. So that's why a unique solution exists for all x. Okay, by the theorem. Okay, very good. Okay, so we mark, be careful, always put the equation in standard form. Okay, as in the case of first order linear ODE, the solution of a second order linear ODE can be written as a sum of a particular solution. Okay, so the particular solution involving the forcing function g of x. This is actually like the function on the right hand side. So the function on the right hand side. Remember, our standard form is y prime prime equals p of x, y prime plus q of x, y equals to g of x. So this is the function on the right hand side. So yh is the homogeneous solution, which is solution to the homogeneous equation, the left hand side equal to 0. Okay. All right. Let's continue. We might as well solve the homogeneous equation first. Okay, so let's solve the homogeneous equation first, and then we can figure out the homogeneous solution, and then we can find the particular solution and add them together. We'll get a general solution for the differential equation. Okay, so in general, how do we solve homogeneous equations? So right now, let's talk about the solution space. The solution space is actually a linear function space of dimension 2. So it's a vector space. Okay, so what does that mean? And can we make connection to the linear vector space of chapter 3 and 4? Yes. Let's see how. So what is a linear function space? So a linear function space contains the 0 elements. So you can see we have the homogeneous. So this is the homogeneous. Okay. Okay, E. Let me figure out why. Okay, so let's show that the solution space is a vector space. Do you remember how do we show that a space is a vector space, a set is a vector space? We show, okay, so for vector space, we show first is non-empty, okay? And then second, we show close under addition, and the third we show close under scalar multiplication. Okay, all right, so let's look at this. Okay, so that because the solution space is the solution of the homogeneous differential equation. What is the homogeneous differential equation? This guy, y double prime plus p of x, y prime plus q of x, y equal to 0. Okay, so first of all, let's check it contains the 0 elements, which is 0. You can see the derivative of 0 is 0, the second derivative of 0 is 0. So when you plug in y equal to 0 into this differential equation, you get 0. So y equal to 0 is the solution. Okay, next, let's check close under addition. Suppose we know two solutions, y1 and y2, and then we want to show that the sum is also a solution. Okay, so because y1 is a solution, it means y1 prime prime plus p of x, y1 prime plus q of x, y1 equal to 0. And because y2 is a solution, we get y2 prime prime satisfy the differential equation. Okay, so y3, how do we know y3 is a solution? So we want to check whether y3 prime prime plus p of x, y3 prime plus q of x, y3, we want to check whether this is 0. So, but this guy is y1 plus y2 prime prime plus p of x, y1 plus y2 prime plus q of x, y1 plus y3 as 2. Okay, so we can split it. We get y1 prime prime, okay, plus y2 prime prime, plus p of x, y1 prime, plus y2 prime, plus q of x, y1, plus q of x, y2. We can actually group the y1s together. We get y1 prime prime plus p of x, y1 prime, plus q of x, y1. Okay, plus y2 prime prime plus q of x, p of x, y2 prime plus q of x, y2. And that equal to 0. Okay. Next, let's check close under scalar multiplication. Okay, so scalar multiplication you have, let's say y1 is a solution, okay? So y1 is solution. It means y1 prime plus p of x, y1 prime plus q of x, y1 is 0. Okay, so in order to check whether y4, so constant multiple c times y1 is a solution, we actually need to check whether so y4, which is c times y1 prime plus p of x, c times y1 prime plus q of x, c y1, is that equal to 0? So that is constant multiple. We can put it outside of the integral, and c we can put it in front, c we can put it in front, and we can put all the c, we can factor out all the c. So we have y1 prime plus p of x, y1 prime plus q of x, y1 equal to 0. Okay, so that's why we have y4 is also a solution. So the solution space, it contains it contains the 0 element, so it's non-empty, it's closed under addition, it's also closed under scalar multiplication. So it in fact is a vector space. Okay, and because it has dimension 2, right? Remember, second order, it has dimension 2, and we need 2 linear independent solutions to form a basics. Okay, then the entire space of solutions can be described as a linear superposition or a linear combination of the basis functions. Okay, so now suppose y1 and y2, they are linearly independent solution to the second order linear ODE. Then the linear superposition is the same as linear combination. Okay, y of x is c1 times y1 of x plus c2 y2 of x. So here c1 and c2, they are real numbers. Okay, so this guy, this linear combination, is called the general solution of the homogeneous equation. Okay, and it describes all possible solutions. Okay, we can also apply the constant, initial condition to find the constant. Okay, questions. What does that mean for two functions to be linearly independent? How do we check for linear independence? Okay, so here is the definition. Very similar to the definitions for vector space. Two functions f and g, they are linearly independent if we have like c1 times f plus c2 times g equal to 0, can be only satisfied by c1 plus c1 equals c2 equals 0. So let me recall what is the definition for like vector u and v are linearly independent if we have like a u plus b v equal to 0 implies a and b are both 0. So it means a and b are both 0, you get 0 equals 0, right? When you plug in, well, that tells us nothing. So that's why the u and v are independent. Same thing here. If you get c1 and c2 are 0 when you plug in, you just get 0 equals 0. It tells us nothing about, so no relationship between f and g. So they are linearly independent. Okay? So now we have one equations to two unknowns, f and g, but we can generate a second equation by taking the derivative of that, right? We have two unknowns, c1 and c2. We need two equations to solve two unknowns. So this guy gives us one equation, but when you take the second derivative, it gives us the second equations. So two equations, we're able to solve two unknowns. Okay? All right, so that's why we have a 2x2 systems. Okay, so here are the coefficient of C1. So these are the coefficient of C2. That's why we put them here and put this guy here. Okay. So with the function, but here we have functions in the matrix instead of numbers. But that's okay. It works the same. Okay, so for a square system, okay, for a square system, it means it's 2 by 2 or 3 by 3. How do we enforce that C1 and C2 equal to 0 is the unique solution? The answer is we require that the determinant of the matrix to be non-zero. Remember, the determinant is not 0. We get a unique solution. Okay, so we have ax equals to b. Okay, so if determinant is 0, then we might have no solution, or we might have infinite many solution. Okay, so that's why here we need the determinant is not 0. What is the determinant? Cross multiply, but you subtract. So that's why f of x times g prime of x minus f prime of x times g of x. Okay, that is not equal to 0. So we call this guy, the determinant of this matrix, to be the Wronskian. Okay, so we call the Wronskian in the ODE. Sometimes we write w of f of x and g of x. Okay. Alright, to solve second-order linear homogeneous ODE, the goal is to find two linearly independent solutions. So let's look at example 5. Okay, so this is example 5, y double prime minus y equal to 0. Okay, part A, show that y1 of x is e to the x, y2 of x is e to the minus x are the two solutions of the above ODE. So part A, we are actually given the solution. How do we check whether they are the solution? Well, we plug it in, right? So y1 of x equals e to the x. Okay, and then y1 prime of x was the derivative of e to the x. It's still e to the x. So when we plug in, the left-hand side is y double prime. Oh, we need y double prime, so let's take one more derivative. It's still e to the x. So e to the x minus y is e to the x, is 0. It's the right-hand side. Yay! So y1 is a solution. How about y2? y2 of x is e to the minus x. y2 prime of x is minus e to the minus x. y2 prime prime is negative times negative is positive. Okay, so the left-hand side is e to the minus x minus e to the minus x. We also get 0. Yay! So y2 is also a solution. Okay, to check a function is a solution, it's very easy. We just plug in it. Okay, but given a differential equation and asks you how to find the solution, this is challenging. Okay, all right, let's continue. Show that these two solutions are linearly independent. Okay, so alright, so how do we show those two solutions are linearly independent? Oh, okay, so we want to set C1 e to the x plus C2 e to the minus x equal to 0. And we want to show the step 4, C1 and C2 has to be 0. Okay, so how do we see? So we have one, this is one equation. We need two equations to solve the constant C1 and C2. So second equation, we take the derivative of both sides. So C1 constant multiple stay here. E to the x derivative is e to the x. And here we have derivative of e to the minus x is negative e to the minus x. Okay. All right. So we have two equations. Now we can form a matrix. So the coefficient is e to the x, e to the minus x. That is the first equation. Second equation, e to the x, negative e to the minus x. Okay. All right. So that's why here we have the system and the Wronskian. Okay, what's the Wronskian? Is the determinant. Okay, so the determinant of those two this matrix. Okay, you can see the first row are the solutions, and then the second row is the derivative of the solution. That's why derivative of e to the x is e to the x. Derivative of e to the minus x is minus e to the minus x. Okay, so what's the Wronskian? Wronskian, you cross multiply, you have e to the x times minus e to the minus x minus e to the x times e to the minus x. Well, you can see here, e to the x and e to the minus x, they cancel, we get 1. Okay, and we get -2. -2 is not 0. Yay! We get a unique solution. So we get a unique solution. But because the right-hand side is zeros, so the unique solution, remember, this is a homogeneous system for like linear system. Okay, homogeneous linear system. So that's why we get unique solution is the trivial solution. It means C1 and C2 are both 0. Okay, so that is why we can say that y1 and y2 are actually linearly independent. Okay. There is another way to solve it. Is actually you consider that matrix and you can solve it by Gaussian elimination. And let's see. Okay, so this is method 2. So method 1 is you can use the determinant. Method 2, you can actually solve the use Gaussian elimination. So method 2, use Gaussian. Oh, sorry, spelled wrong. Elimination. Okay, so we have e to the x and e to the minus x, 0. And we have e to the x and minus e to the minus x, 0. Okay, remember here, because the first entry, 1 entry, and the 2 entry are the same, so we can use minus row 1 add to row 2 to make it 0 there. But because you're working with functions of numbers, you have to be very, very careful. So e to the x minus e to the x is 0, minus e to the minus x minus e to the minus x is minus 2 e to the minus x. And we get 0 here. Great, we have echelon form. So first column is the coefficient of C1, second column coefficient of C2, and then this is the right hand side. What does the last row means? So the last row tells us that minus 2 e to the minus x equal to 0. But do you know, like, e to the minus x, this is what e to the minus x looks like, and it's always positive. So oh, I almost forget very important thing, my C2. Okay, yeah, because e to the minus x cannot be 0, so it forces C2 be 0. Okay, and then we plug it back into the first row. So the first row tells us that e to the x C1 plus e to the minus x C2 is 0. Because C2 is 0, this guy is gone, so e to the x and C1 is 0. Because e to the x is not 0, so C1 has to be 0. So we also get C1 and C2 are both 0, so we get y1 and y2 are linearly independent. Okay. All right. Okay, so we have shown 2 methods about showing the solutions are linearly independent. Okay. All right. So let's continue the next video in part B.